Swayam Prabha. Digital India. Educated India.
Welcome back, students. In the last class, we were discussing about the internal and external mass transfer limitations in immobilized cell systems or immobilized enzyme systems. And while characterizing the internal mass transfer limitations in systems, we assumed different reaction kinetics, in which we started with the zero order kinetics, and then today we are going to assume a first order kinetics and see how does the efficiency factor or the substrate profile in the presence of diffusional limitations changes with the radius of the pellet. So, if you can see on the slide, the first order kinetics, it will be a linear function of the substrate. So, because here the rate of reaction is in terms of the substrate, so the sign is negative here for the rate constant, and Cs stands for the concentration of the substrate. Now, in the same double differential equation where we did a shell balance for the substrate diffusing in from the surface of the pellet till the inner core or of the immobilized system. In the same equation where we were describing the net accumulation rate of the substrate, there if you see equation 3.24, it has been converted in the terms in dimensionless variables of xs shown here and r dot. Now, xs is has been made a dimensionless variable or a ratio of Cs to Csb, where Csb stands for bulk substrate concentration. Your r dot is a ratio of small r to capital R, where if you remember, the capital R was the radius of the pellet or that immobilized shell, and small r is the distance travelled by the substrate from the center. And phi, which is a club of constants here after rearrangement. So, these constants include the rate constant, the reaction rate constant, and the diffusivity with the radius of the pellet. Now, phi stands for this constant, which is called as Thiele modulus. If you can see in this equation here, which I am underlining, it is a measure of the reaction rate to the diffusion rate. So, again with the changing values of phi, phi being low or high, we can determine whether the reaction rate is high or the diffusion rate is high. Then the boundary conditions in terms of Cs and R have been now changed in terms of the dimensionless variables xs and r dot. So, as dCs by dr was 0 at r tending to 0. So, xs is called again will be bounded at r dot nearly 0, and xs will become 1, which means when Cs is equals to Csb at what point? At the surface of the pellet, which is r dot is equal to 1, where r is equal to capital R. Now, in order to solve this differential equation 3.24, again like we did for zero order kinetics, a substitution has been done in terms of alpha dot, where alpha dot stands for R dot times XS, and then we simplify the double differential equation and then we integrate it twice to get XS in terms of R dot. Now, as XS must be bounded when R dot approaches 0, so therefore C1 has to be chosen as 0, and using the second boundary condition we can determine the value of C2 as 1 by sin h 3 phi. So, if C2 is 1 by sin h 3 phi, your XS then becomes a function of R dot as shown in the equation 3.3. So, if we make a plot between XS and R dot with varying value of Thiele modulus, we can see how Thiele modulus affects the substrate profile inside the pellet. So, if the Thiele modulus is very low, effectively meaning that the rate of enzymatic reaction is slow compared to the diffusion rate, then the substrate would diffuse into the core of the particle, which will result in fairly flat distribution as shown here by the blue line. On the other hand, for higher values of modulus, like let us take phi is equals to 5, this would mean that the reaction rate is much faster than the diffusion rate. So, most of the substrate will get consumed in the reaction near the particle surface itself before it diffuses in, and therefore, you see a sharp decrease in the substrate profile as it moves inside. Now, in order to find an expression for the efficiency factor in such a system, then efficiency factor, if you remember, it is the ratio of the actual reaction rate to the reaction rate without diffusional limitations. So, without diffusional limitation would mean that maximum mass transfer. So, maximum mass transfer rate would be what? Will be KCSB, because there is no diffusional limitation. So, then whatever is at the surface should be able to reach to the inner core. So, maximum rate would be KCSB, and the actual rate will be equal to the diffusional rate here at R dot equal to 1. So, we will be using the fixed law of diffusion. So, for the entire pellet we will be calculating. So, therefore, the R dot value will be equal to 1, and we will multiply and divide the dCs by dr with CSB and R, and then taking it inside the differential function being a constant and converting it into a XS and R dot form. So, then outside we will have the CSB and R, the diffusivity constant, and your area of the particle and the volume of the particle. So, this would be your reaction rate. So, if we solve this, the expression for the efficiency factor comes in the form of Thiele modulus. And now, if we try to visualize how Thiele modulus can affect the efficiency of the immobilized system, then what we can find is that for different types of reaction kinetics, as the value of phi is less than 1, the effectiveness factor is nearly equal to 1, which is the case when the rate of reaction is not getting slowed by the diffusion process. On the other hand, if the Thiele modulus is becoming greater than 1, then the effectiveness factor is found to be inversely related to the Thiele modulus. So, as the Thiele modulus will keep on getting increased, the efficiency factor is going to go down. Now, if we take a Michaelis-Menten enzyme kinetics or reaction kinetics in the enzyme system, we know that the reaction rate can be given as shown in equation 3.33 as Michaelis-Menten kinetics. So, now substituting in place of the reaction rate here, also further changing the Cs and the R in terms of the dimensionless variables Xs and R dot. So, we have Thiele modulus and an extra constant called beta, which is defined as CSB by Km. Km stands for the Michaelis-Menten constant. So, if you do the rearrangement of the second order differential equation and do all the substitutions, bring all the constants together, then the Thiele modulus in this case gets slightly changed in comparison to that with the first order kinetics, where now inside the square root you will find we have the Michaelis-Menten constant, the diffusivity and the maximum reaction rate. Now, this is a non-linear function in excess. If you see, notice equation 3.34. It's a non-linear function in excess, so it cannot be solved analytically. So, we use various numerical techniques, and in order to simplify it, we again do a substitution, converting dxs by dr dot as y, and then this is equation, the earlier equation gets converted 3.35 gets converted to a single differential equation form as shown in equation 3.36, and similarly your boundary conditions can be changed in terms of y with r dot, where y now becomes equal to 0 as excess was bounded. Let us assume that there is a critical radius r beyond which the substrate is not able to diffuse in, so it is bounded. So, your r dot then in that case becomes Rc, which is the critical radius, by the total radius of the pellet, the surface, and at xs is equal to 1, which means at the surface where the substrate concentration is equal to the bulk concentration, this is happening at the surface. So, therefore, r dot value is 1. So, the boundary conditions remain the same, it is just the change in the variables. And in this case, the effectiveness factor can be represented as the actual reaction rate and the reaction rate in the absence of any diffusional limitations. So, if there are no diffusional limitations, the substrate which is available for reaction is your bulk substrate concentration. So, it has been substituted in the Michaelis-Menten equation for maximum reaction rate without diffusional limitations, and the numerator is using Fick's law for the reaction rate. So, as the value of the effectiveness factor is a measure of the extent of diffusional limitations, let us see some cases. If the effectiveness factor is less than 1, this means that the conversion is diffusion limited, whereas if effectiveness factor is nearly 1, this means the conversion is limited by the reaction rate and the diffusional limitations are negligible. And eta in turn is a factor of Thiele modulus and the function beta in this case. Now, if we want to use this as a generalized equation and try to find the conditions for the 0 order and the first order reaction rate. So, if you substitute the value of beta as very large value, which means beta tending to infinity. So, beta was CSB by Km, isn't it? And beta is very large, which means the substrate is in excess. So, it becomes a 0 order reaction. Then your efficiency factor is nearly equal to 1 for a wide range of Thiele modulus. Now, if you remember to visualize this, what was Thiele modulus? The Thiele modulus was maximum reaction rate to the diffusion rate. So, for a wide range of Thiele modulus, the reaction rate will be higher than the diffusional rate because the substrate is in excess. So, your efficiency factor will be nearly equal to 1, and this range of phi is given as between 1 to 100. Now, let us take the case for the first order reaction rate. So, for the first order reaction rate, beta tends to 0. So, your beta was CSB by Km. So, beta is tending to 0 here. For high values of phi, your eta can be given as a function of hyperbolic functions of phi, and beta is a very small value. So, now let us see how can we use all these informations in a practical scenario. Now, the points which we must keep in mind when we are designing immobilized systems for maximum efficiency, because internal diffusion will limit the enzymatic reaction rate, the constants, the Vm and the Km, in such immobilized systems, they will not be the true intrinsic rate constants, but what we will measure through the experimental data would be the apparent values. Now, in order to obtain the true rate constants inside the immobilized systems, the diffusional limitations, they should be eliminated by doing what all things? By using small particle size, having high degree of turbulence around the particles so that the boundary layers are reduced, or having high substrate concentration. Now, while designing immobilized enzyme systems using particular support, the main variables are the maximum reaction rate and the radius of the pellet. Now, maximum reaction rate would in turn be dependent on the concentration of the enzyme. Now, when the substrate concentration Km, which is the affinity of the enzyme towards the substrate, and D stands for the diffusivity of the substrates, this we assume are fixed, the given values, because the substrate is given. So, the particle size is what which can be manipulated or designed, and the second is the enzyme concentration which is being immobilized in the system. So, the maximum reaction rate is determined by enzyme activity and the concentration inside the support. So, high enzyme content will result in high enzyme activity per unit of the reaction volume. However, this will lead to low effectiveness factors because all the substrate will quickly get consumed near the surface. Efficiency factor will reduce because whatever is present inside will be devoid of the substrate. Whereas, if there is low enzyme content, it will result in lower enzyme activity per unit volume, however, high efficiency factor. So, for maximum reaction rates, what should one do? The particle size should be kept small and the enzyme loading should be optimized, so that although the enzyme activity per unit volume is being optimized, the size of the particle is being designed so that all the substrate is able to reach and get converted with the enzymes present in the inner core.